Okay, so all these different acronyms that we mentioned, but it's really all about how to make decisions and making good decisions. Here, this is a small picture of the brain there, but the brain helps us with making a lot of decisions. And I found somewhere on the net that we make around 35,000 decisions in a day. I think it sounds quite a lot, but I said at least well above 10,000 decisions per day. Most of them are very small. It can be about pressing this button or picking up a pen or things like that. But there are semi-unconscious. But then we make around 150 informed decisions per day. It can be what to watch on Netflix. We look at different options and we select the one that we would like to look at, or it can be what we want to eat or what we want to wear or something like that. It's quite interesting how we make those decisions, but it's not what we'll focus on today either. It's about those very few key decisions that have very big impact in a private perspective. It can be on our quality of life, maybe the education that we take, or where we choose to live, or what car to buy. It affects our quality of life and also safety and comfort and flexibility, and maybe also our status. And also it can affect our personal economy. So we need to figure out what is most important for us. Is it have a fast car or a spacious car or a motorcycle that can cut through the traffic? And do we have to have high horsepowers or good fuel economy and so on? So for those decisions that are more significant, we probably look for more information. We want to learn more before we make a decision. And we should be careful not to make those decisions the same way as we do with those above. It's quite spontaneous and we just think about what we want. It's quite good to make some research and some calculation and gather some information first. And this is the type of decisions that we will focus on in these 3 days. But not on a personal, private plane, but more on a national scale impact. Because the decisions that we make within lifecycle management of the defense systems really have impact on the defense of our nation. We want to have systems that contribute in the best possible way to our defense capability, the readiness, the responsiveness, how flexible we are to adapt, robustness and endurance in case we would happen to have a conflict and so on. And also, of course, it affects the total budget of our nation as well. There are many of them very, very expensive. So, of course, even more the reason to have well-founded decisions and not make spontaneous decisions without a good foundation. The other thing to consider is that normally we have long life cycles, and it's a long time between we make a decision and we see the consequences. So all that is all good arguments for getting good decision support. And the reason we are here and talking about this is that we, of course, offer modeling and analysis as one way to provide that type of decision support. This is what OPUS Suite does, to give decision support for all these type of situations, to evaluate and compare and predict what's going to happen based on our choices, optimize and challenge our solutions to make sure that we always strive to the best possible decision for the time period and the objectives that we're looking at. Okay, so if we take a helicopter as an example, and we want to ensure a defense capability, if we read the news and so on, the typical discussion maybe is how many submarines or helicopters or ships or tanks or so on a country will acquire, or how many we have, and what is the total investment budget and so on. But in our area, lifecycle management and Ram-C, we have to think a bit differently. We have to think about what are the operational requirements for the helicopter. What are the scenarios that we will be able to handle? what readiness levels are required during peacetime, and during high alert situation, and during conflict. How does that impact the reliability requirements that we should have on this helicopter? How can we translate it into maintainability requirements, and what are the downtime drivers that will impact our readiness and so on? And that in turn will of course have an impact on what are the maintenance volumes, how many repairs do we expect, and what is the most beneficial maintenance? How can we make sure that we can quickly repair and get the systems up and running again when there's a failure, all those things. And again, those have to be balanced against the cost. So we have to see what is worth the investment, what are the cost drivers, where can we try to find ways to reduce the cost, and we can probably not get everything that we want, so we have to make trade-offs. What is the best bang for the buck, or the most cost-effective decisions to make to reach objectives that we have. And then once we have the systems in operation, we have to continue looking at how they will be able to operate, what improvements are possible, evaluate what readiness levels can be expected, and do we have enough spares? Do we have security of supply that we can handle resupply of resources, and so forth. So lots of different decisions and issues that we have to consider and balance against each other. So that's the whole background and reason for life cycle, or analysis-based life cycle management, and for doing modeling and analysis. So then we start with, we want to make decisions, so we need to figure out how this helicopter works. So we start by doing a model of that. There's a lot of talk now about digital twins. So if you make a really detailed description, it will be a digital twin, or it can be a rough model to build a digital image or abstract picture of what this helicopter looks like. What parts does it consist of, and how often do they fail, and what do they cost, and all those things. We build a model of that. But to get a full picture, it's not enough to build a model of the helicopter. We also need to describe the support system. What are the repair capabilities? What are the lead times? How long does it take to transport? What are the costs? How many people do we have, engineers do we have available, and what equipment do we have, and where is that located, and so on. We also have to build a model of the support system. And finally, of course, we have to understand how the systems will be operated. So we build a model of that as well. And if you have worked in OPUS Suite, I think you feel quite familiar with this. That's really what we build with all that information that you have in OPUS Suite. So that's kind of the modeling that you require to understand and make decisions about this, because you need to have a system perspective. It's not enough to just look at the helicopter on itself or alone. You also have to understand the other areas. So how much detail do you need? Well, it depends very much on what type of decision you want to make and where you are in the life cycle. We normally have this picture as a metaphor, which is, I think you recognize, as a crash test dummy. It's a very good model for that purpose, where you want to see what happens when you crash a car. It doesn't have any organs, or it cannot move, it doesn't have any hair or no eyes and so on, but it's very, very good for that purpose. It has the right weight, has the right dimensions. If you're a man, there should be also a female crash test dummy, of course, but for this type of evaluation that they want to do here, this is a good model. So it's really a good way to explain. You don't need all the details. Depending on what type of decisions you want to make, you can want to make sure to describe the relevant features and parameters with sufficient amount of detail. So it's not always the exact answer you want. It's an understanding which is the best direction to go. It's really engineering decisions. So that's what important to remember. We should not limit ourselves to only make analysis when we have all the information. We have to make best possible use of the information that we have to make good decisions. Okay, so once we have built a model of all this, we can then make analysis. And this is, I think, a diagram you may recognize from OPUS Suite, where you have effectiveness on one axis. It can, for example, be availability or service level or something like that, and you have cost on the other axis. And then, of course, for each scenario, you have a cloud of possible solutions. These are all the possible outcomes that we can have depending on your selections and how you build your helicopter, how you build the support system and the operations. You can end up somewhere in this diagram. So if you're unlucky, you end up here, where you pay a lot, but you don't get high performance. So of course you want to find the solutions that are on the upper edge of this cloud. And that's really the curve that OPUS calculates for us, where we have all solutions are really optimal, but you pick the solution that gives you, that meets the requirements. So this, I think, can summarize very much what you're looking for always as a Ram-C engineer, to find solution that gives you the best possible total performance and the best possible economy during the life cycle. But it's not always that you can pick the optimal solution. Sometimes you have an existing stock and you're doing a evaluation and you see, well, this is where the performance I have at the moment. So then maybe you want to also evaluate what is the impact of my different possible decisions here. If I make a change, how will it impact my performance, or how will it impact my cost? So this is really the type of decision support that you want to get. And when you optimize, you can see what is the most cost-effective improvements. So this is just to summarize, I think, what we're all trying to achieve. Those diagrams are also part of OPUS 10, and then each point only symbolize one solution. Behind each point there's a whole collection of different results and so on, where you can dive into what that solution will result in terms of cost and performance over time and things like that. So it gives you this possibility to evaluate fleet readiness, mission effectiveness and cost and so on in many different ways. So this is really what we mean with modeling and analysis. In this case we had a helicopter example, but OPUS Suite is widely used in all branches of defense. So these are all examples of programs that are using actively OPUS Suite. Most of these have been using it for a long time, and quite a few of them are used both on the government side and the supplier side. So I think that's is helpful for you to know that it's very flexible tool that you can use for any type of technology and any type of or any part of the life cycle and any complexity when it comes to both operations and the maintenance concept and so forth. So during the life cycle, we have such a long list of different decision points, major decision points that we need to make. From the early phases, the decisions on the requirements, for example, will have a very big impact on what systems we will develop and how they will perform. Then when looking at the design, we make a lot of trade-offs between parts and the design choices and so on that will have a big impact. Then, of course, when we come later on, we will have the PBL, which is very important to get a lot of decision support done and so on. So a lot of different key decisions that will have big impact on both performance and cost during the life cycle. So when we have a model in place of the helicopter and the maintenance solution and the operations, even though it's quite rough in the beginning where we have very little information, we can work iteratively, get new information, understand what area is most important for us to focus on, get new data, expand the model, get better and better accuracy, and get the information we need. And also, if we have a model in place in the early baseline model, it will be quite quick to make the adjustment needed for a new type of decision support. So it's a big benefit to have an active, proactive approach to this rather than developing a new model and a new approach for each new question when it comes up. If we have that baseline in place and we have a model that's continuously updated and so on, it's quite quick to get the decision support that we need. I think this is probably a diagram you may have seen before that shows also the different life cycle phases of a system, and where the cost, of course, comes mostly during the operations and support, and both the development and operation and support. But the decisions that decides on what those costs will be are made very early. So the committed share of the LCC is high already in the procurement phase, and the ability to influence the overall life cycle cost goes down quite quickly. I think this is an important concept behind Ram-C and ILS, that start early and make sure that you always try to understand the impact of your decisions, even in the very early phases. But it's important then to also emphasize that to keep the costs within its projected size, we have to continue having that focus. And every big new decision, maybe about an upgrade, or we want to start using the systems in a new way, or we want to change the maintenance concept and so on, we always also have to continue having that focus on life cycle cost. And this concept is, I think, very applicable as well on performance. That the decisions you make early in the life cycle will also have a big impact on the performance during the operation and maintenance phase. So I think this is a very good example to illustrate that. I think you recognize this aircraft, it's the F-35, and this slide is about a report that came out last year from the US Government Accountability Office called GAO. And it was made quite a big impact, this report, because it talked about the capability rates for the US part of the F-35 fleet that were as low as 55%. And then it did an investigation of what the reason was. And of course, even though it was very low, the costs for sustainment were very high. There are 75% of the estimated total LCC. So the total LCC is about $1.7 trillion, so it's quite a big budget. And 75% of that was sustainment cost. And still they had issues then with mission capability rates. They found one important reason for this was long turnaround time for the repair of spare parts. The projected number of days was 60 to 90, and then instead they had about, on average, 141 during 2022. And the backlog was growing, so the number of components that were waiting repairs was increasing, and that was cause for 27% of the unavailability during 2022. So then, of course, it's interesting to, so they had to, instead of repairing, they had to purchase new spare parts because of the very long backlog. So the main reason for this was lack of depot capacity. And it was a decision that was made very early in the F-35 life cycle. In the 90s, they made a decision about the maintenance concept, that it was they were going to outsource all the repairs. And then to save some time and money, they said, well, then we don't need the technical documentation. That will be up to the supplier to have that. So there were no requirements at all on that technical documentation. So this means that it was very difficult to do anything about these issues. They could not, when there were more and more aircraft, I think they have around 3,000 F-35s will be at maximum operating.
Excuse me.
Yes.
Please move to right.
Oh.
So yeah, because you hide some.
Yes.
I'm sorry about that.
No, thank you very much for telling me. That's good. Is this better?
Yes.
Yeah.
Thank you.
So this meant that when they were scaling up and getting more and more aircraft, they could not scale up the repair capabilities in the same rate. And they were very dependent then on those decisions that had been made early on. And also the subcontractors did not have documentation because they didn't need to develop it according to the contract. So now, of course, there are a lot of efforts done to improve that. You could say, well, just do spares optimization and buy more spares, but they, of course, they don't want a dimension for a situation that we have very, very long lead times. Now they want to build up, and they will, of course, be able to handle that, but it will be much more expensive than if they had done this from the beginning. I think it's complex. We cannot say now. It's easy to say afterwards that this is how it should be done. But I would say that if there had been some analysis early on to compare this, they would have seen this earlier on. And this is the type of decisions that really you use OPUS Suite for, to check the maintenance concept and make rough models and check out the consequences of these different decisions early on. So I think this is a good example of a strategic type of decision that had very, very very big impact. Then we also talk about tactical type of decisions. So here we have another example where we have, this is a fictive example, it's not a real life, but we have made real life projects that are very similar. So here we have two different aircraft systems, one manned and one unmanned. We have a 30-day scenario, 3 different phases and 6 different mission types. And I don't know if you can see in the back, but on the x-axis there is number of days, so 30 days. And on the y-axis there is number of systems in use, so you can see in the beginning